Hello and welcome. I'm Katherine Blundell, Gresham Professor of Astronomy. The title of my talk today is Perceptions, Expectations and Discoveries. I want to talk about the business of discovery in science. How does discovery happen in science? The problem is, how do we know what to discover until we've discovered it? And how do we go about knowing how to discover it until we know what it is? This question is relevant to the discovery of celestial phenomena far from the planet we call home and far from the galaxy we call home, as it is to discovery in, for example, modern medicine. More of this later. As I emphasise to my research students in Oxford, there are no answers in the back of the book where research is concerned. It's actually worse than that. There are no questions in the front of the book. Something that's key to advance in scientific discovery or an advance in research is being able to ask the right questions. Albert Einstein, the Nobel Prize-winning German physicist, had this to say: "If we knew what we were doing, it wouldn't be called research, would it?" And this is what the French microbiologist Louis Pasteur had to say. In full, in the field of observation, fortune favours only the prepared mind. This Frenchman is the person to whom we owe our modern understanding of the link between germs and disease. Back to astronomy. There are many beautiful and memorable patterns in the night sky. I'm showing here the shape of Orion, a very famous constellation known in both hemispheres. Being observant and being familiar with what's happening around us are, of course, very important. In the context of the global jet watch that I described in my third lecture entitled The End of Matter, we are so pleased that teenagers around the world come to appreciate more the beauty and patterns of the night sky. One way of appreciating the beauty and patterns of the night sky is to look up at it constantly with an all-sky camera. Such a camera usually includes a fisheye lens, which gives you a view of the entire 2 pi of sky above your horizon. Here we see it at night with stars moving across it, and then daylight comes, the sun rises in the east, rises up to the highest point in the sky for noon, and then sets in the evening in the west. Nighttime comes again, and the stripe of stars you see moving from left to right is the galactic plane, and maybe you can make out Orion in that. And now we have morning again. The sun rising through the bright blue sky above the chilly school observatory that's part of the global jet watch, and it sets in the west in the evening. And the stars rise again. Here's the galactic plane, Orion riding through the sky, and clouds really do spoil a good night's observing, let me tell you. Let's think more now about the history of astronomy and discovery. What did our ancestors know and how did they learn? In recent weeks, a good many of us have become very expert in video conferencing via the internet. In contrast, our ancestors had developed a completely different set of skills. They were vastly more skilled at knowing and recognizing the night sky than we tend to be. For all our modern astronomical infrastructure, many people don't know the night sky at all, and many people can't see the night sky at all because of so much light pollution. So, besides Orion, what else is up there in the sky that was known to our ancestors? The Pleiades is a very beautiful and famous set of stars in the night sky. Where are they and what do they look like? Well, if you take the constellation of Orion and trace its belt upwards to the right, going via Aldebaran, which is a great big bright star just to the west of Orion, then you'll see a beautiful group of stars called the Pleiades. The Pleiades have a right ascension of nearly 4 hours, so they come back to the night sky in the last few months of our calendar year. This is, of course, crop growing season in the southern hemisphere. Prior to the calendars we use these days, in Latin America, the reappearance of the Pleiades in the night sky was the calendrical cue for crop planting to commence. Such was the familiarity of the Pleiades in bygone times that they appear in all sorts of literature. In the Old Testament, the writer Amos, a shepherd with a sideline in the horticulture of figs, was keen on social justice and communicating God's disdain when this did not happen. In the middle of a powerful rant against those who cast aside justice, Amos draws a contrast with the beautiful things in the night sky, the beauty of a new dawn, the beauty of Orion and the Pleiades, the blessing of rain on the land, with their objectionable social injustice. Now, such a skilled orator wouldn't be referring to celestial objects by name in the night sky if they were not actually part of the lexicon 7.5 centuries BC. In addition to being an object of extreme beauty in the night sky, the Pleiades were an important tool in the toolkit of the early ophthalmologist. The number of stars that somebody could see in the Pleiades was an excellent discriminant of how good their visual acuity was. Many people with good eyesight can make out 7 stars, hence their alternative name, the Seven Sisters. But some with exceptional visual acuity can make out more. King Lear and the Fool have a discussion about how many stars it is thought there are there. Of course, if instead of using just human eyes to observe the Pleiades, you use a telescope and a camera, then you appreciate just how many stars there are in this star cluster. This beautiful image by my colleague Steve Lee in Australia shows that there are a great many stars, some 3,000 in number in fact. And these stars, some of them are surrounded by nebulosity. The interstellar medium surrounding this bright star Merope was discovered in 1912, the same year as the sinking of the Titanic. So, as I said, this star cluster contains 3,000 stars, and it's quite close to Earth, or at least relatively speaking. It's only 440 light years from Earth. And from one side to another, the physical extent of this star cluster is only about 13 light years. John Mitchell, the Yorkshire rector, whom we met in my 3rd lecture, The End of Matter, in the context of early thinking about the concept of black holes, pointed out, again way ahead of his time, that so many stars in the same place in the sky couldn't be random, and therefore, on the basis of a probabilistic argument, he deduced that these stars were likely held together by gravity in what we now know as a star cluster. So here are the 7 brightest stars in the Pleiades cluster. This is Alcyone. The number after the name is the magnitude of the star. The smaller the number, the brighter the star, and the more easily it is seen by human eyes. The next brightest star is Atlas, with a magnitude of 3.6. Then it's Electra with 3.7. Then it's Maya with 3.9. Then Merope, I discussed a moment ago, with a magnitude of 4.2. Then Taygeta, with a magnitude of 4.3. And the 7th one, Pleione, has a magnitude of 5.1. If you can see more than 7 of these stars when it's up in the night sky, then you have exceptionally good eyesight. So science relies on and is refined by evidence. We don't use the word proof in science research. Proof is a word that belongs to mathematics. And in connection with exploring mathematics further, I commend to you the lectures by the Gresham Professor of Geometry, Chris Budd. Back to our ancestors. Whenever I consider the science developed by those who lived before us, I am humbled and amazed by all they achieved. Way ahead of any telescopes, what people who lived centuries ago figured out is remarkable. For example, consider the nature of the rocky planet we live on. How did our ancestors come to discover even what shape it was? Different pieces of evidence played their role. Looking around, in certain parts of the world at least, for example, in a famously flat place such as the Netherlands, the Earth looks flat. How is it that people came to think differently? Different types of evidence came in different ways. For example, evidence from geometry. Over 2 centuries before Christ, the polymath Eratosthenes, who was born in what we now know as Libya, considered the shadows cast by a vertical rod stuck in the ground at Alexandria and at Syene. And he considered how long were the shadows from these vertical rods at particular times close to the local solar noon. Solar noon is when the sun is locally at its highest point. And Eratosthenes got a value for the circumference of the Earth, which was within 1% of the modern accepted value. There was also evidence on the shape of planet Earth from reporters. For example, the Italian explorer Christopher Columbus and the Portuguese explorer Ferdinand Magellan. There was also evidence from useful models. Gerardus Mercator, born in what is now Belgium, developed a projection model of a spherical planet's surface on a flat bit of paper. And this revolutionized navigation. And this particular projection, the Mercator projection, is still used in nautical charts today. More recently, of course, we have the luxury of direct evidence from photographs. So evidence in different ways of the shape of this planet, built up in different ways by different people at different times. And if you're impressed that Eratosthenes, some 22 centuries ago, could discover and calculate and quantify the sphericity of this planet, calculating the circumference of the planet he was living on, then I think you'll be even more impressed with this. About a century later, the Greek astronomer Hipparchus deduced that the axis about which the planet Earth is spinning, in other words, the line joining the North Pole to the South Pole, changes its orientation with respect to the distant sky background, tracing out a cone shape with a semi-angle of about 23 degrees. To discover this physical redirection is impressive, all the more so when you consider that the timescale for the cycle through that precession is 260 centuries. And this was all calculated and deduced in the century before Christ. This picture illustrates the phenomenon of precession that I'm talking about. At present, the spin axis of Earth points towards Polaris, the pole star. But in half a precession cycle's time, in 13,000 years, the spin axis of Earth won't be pointing at Polaris, it will be pointing at Vega. How did Hipparchus figure this out? Well, he measured the exact position of the bright star called Spica and a bunch of other bright stars. He then compared his positional measurements with data from earlier observers. And he concluded on the basis of these comparisons that Spica had moved about 2 degrees relative to the autumnal equinox. And so he was able to deduce that the rate of precession that he had inferred was no less than 1 degree per century. Is it the case that other planets precess? Well, yes, they absolutely do. I've assembled here a table of how much some of our favourite planets actually precess by. For Mars, the cone angle is 25 degrees and the timescale is 1,780 centuries. For Jupiter, the cone angle is a mere 3 degrees and the precession timescale is about 5,000 centuries. For Saturn, the cone angle is 27 degrees, near enough, and the timescale to complete an entire cycle of precession is 18,000 centuries. Very long timescales indeed, but measurable and calculable. And so it's the case that other stars have their own pole stars. So if the pole star of Earth is Polaris, the pole star of Jupiter is called Zeta Draconis, the pole star of Venus is called 42 Draconis, and the pole star of Mars is very close to Deneb. Now let's consider something else that ancient peoples had a deep understanding of, how the moon moved relative to the sun. Now it's a remarkable coincidence that although the moon is much smaller than the sun, it's got a much smaller radius, it's much closer to Earth than the sun is. And the remarkable coincidence is that the relative distances and sizes are such that the moon subtends the same solid angle as the sun. This means that there are times when they are appropriately lined up when the moon can exactly block the sun. And that's when we get solar eclipses. Solar eclipses happen at new moon. What are the earliest known solar eclipses? Ancient Chinese astronomers were among the most persistent and accurate observers of celestial phenomena. Now, astronomy was very important to the ancient Chinese. It was important to the imperial rulers because they cared about calendars because of the importance to agriculture and feeding the population. The records of the ancient Chinese astronomers were meticulous, and we make use of them even today. And these record a solar eclipse back in 2137 BC. This eclipse was predicted, almost, nearly. It is said that two of the royal astronomers, He and Ho, almost predicted the eclipse but got the day wrong, and on the day when the eclipse did happen, they had been partaking of alcohol, and it did not end well for them. I'm not the first Gresham Professor of Astronomy to have developed a taste for eclipses. Christopher Wren made observations of the solar eclipse in 1654, in Oxford, in fact. This picture shows the path of totality for the eclipse in 1654. It actually passes through Skye and Inverness. It didn't go through Oxford. This is what the eclipsed sun would have looked like as viewed from Oxford during the solar eclipse of 1654. So the 9th Gresham Professor of Astronomy, Christopher Wren, after enjoying an eclipse, lived through the plague of 1655. I think it must have been very frightening to have lived through that particular plague with no understanding whatsoever of the role played by germs and how diseases could have been spread. In that plague, between 15 and 20% of the population died. It is thanks to Louis Pasteur that we have a modern understanding of germs. This is now the path of totality for an eclipse in 1900 that was actually filmed, it was the first one to be filmed, by Neville Maskelyne. He was an amateur filmmaker and he travelled to North Carolina for this total solar eclipse. It was actually 120 years ago next week. The footage from that has been digitised by the BFI with the Royal Astronomical Society. I'm going to show you now a movie of the footage shot by Neville Maskelyne in 1900 of that solar eclipse. Now his camera couldn't track the sun, but some clever alignment software developed by Brian Knight does a pretty good job of aligning some of these rather blurred images. Right now it's during totality and we can see the corona of the sun, and then a short while afterwards the sun will appear on the left, peeping round, giving what we know as Baily's beads. As the sun gradually appears, we see it in a crescent shape on the left, emerging in all its beauty, becoming dangerous to look at once again. So here the sun begins to emerge in its little crescent shape. This was all done with film, which is even more impressive. So this is a movie of an eclipse from 120 years ago. I'm now going to show you a movie of an eclipse that I recorded, thankfully with a digital camera, not with film, in the eclipse in 2017. I'm again grateful to Brian Knight for the alignment software that he designed and developed, which made this possible. As the moon gradually passes in front of the sun, it eats it, and we reach the point of totality, and then that's when it's possible to see the corona of the sun and to see its prominences, shown here in pink. It's only when the moon actually blocks out the sun that it's safe to look at it. And this image from another eclipse taken during totality in the eclipse last year, viewed from a beach near La Serena in Chile, the extent of the solar corona can be seen. It's during totality, so nobody watching the eclipse at this point will be wearing personal eye protection, because the moon is protecting us from the sunlight, acting as celestial sunblock, if only transiently so. Totality at this location for this eclipse lasted 2 minutes and 17 seconds. The Greeks had the preconception that celestial bodies were perfect, unchanging, and describable by mathematical models. From this idealistic premise, they observed, absorbed, and modelled patterns and rhythms they observed in the night sky. And these patterns and rhythms included eclipses. Such were their expectations and their expertise, and expertise here is not merely in mathematics but also in engineering. They built an analogue computer called the Antikythera, which predicted eclipses. Now the remains of this machine were found rather decayed and covered in seaweed in 1901. The structure and the design were analysed and deconstructed by Mike Edmonds and Tony Freeth at Cardiff University, using modern techniques such as X-ray tomography to figure out the details of the Antikythera mechanism. And by details here, I mean its 37 gear wheels. Back to discovery. Do we see what's there? And how do we see what's there? Sometimes we do know what we're looking for. Theoretical predictions enable us to refine our searches for scientific discovery. And a particular example that comes to mind here is the discovery of gravitational waves. I will be covering this in my Gresham lecture next academic year, entitled Cosmic Vision on Spacequakes. But for today, I would just mention that this particular discovery required more patience and tenacity by far than the vast majority of research projects, which in any case require quite a lot of patience and tenacity. Discovery. How do we see what's there? Context is everything. Patience and attention to detail are crucial. Having a prepared mind, understanding the context is absolutely key. Now, the Chinese records excelled in recording celestial positions and patterns and rhythms with meticulous accuracy. Not only did they measure the positions of stars, not only did they develop expertise in predicting eclipses, but in addition to patterns and rhythms observed by the Greeks and others, the Chinese had a superb track record in noticing, observing, and measuring sudden and stochastic changes in the night sky. As I said earlier, they were motivated to do this because of the importance of calendars to agriculture and horticulture. Astronomical calculations based on the actual movements of the sun and the moon which included, of course, and made possible eclipses, were how the Chinese calendars developed. But mathematical calendars, the sort that were used in the West, were based on the average lengths of solar years and lunar months, and these could not include eclipses. But in fact, a very symbiotic collaboration between the Chinese and the West flourished because of a shared enthusiasm for eclipses and their importance. I'm talking about Matteo Ricci, who was the first Westerner to be admitted into the Forbidden City in Beijing. This was in 1601, and he was granted that honour because of his expertise in predicting eclipses. There was a beautiful friendship that grew up between Matteo Ricci and Zhu Guanqi. They translated Euclid's Book of Geometry, into Chinese, and they translated Confucian works into Latin. This is an early example of international and cross-cultural collaboration. International and cross-cultural collaboration is very fruitful, and it's a much cherished characteristic of modern scientific research. Clearly, it goes back for centuries. So, speaking of meticulous attention to detail, the ancient Chinese astronomical records not only measured the position of stars, not only did they develop expertise in predicting eclipses, but in addition to patterns and rhythms observed by the Greeks and others, they had a superb track record in noticing, observing, and measuring sudden and stochastic changes in the night sky. The Chinese gave special names to the new phenomena that they noticed appearing in the night sky. An example of Chinese discoveries of new stars was given the name Broom Star. I'd like to show you now a modern example of what the Chinese meant by a broom star. So we're looking now at an image of a very recent comet known as Comet Swan. This was imaged by Steve Lee. Let me just explain what we're looking at here. In the top right of the image is the head of the comet, or its nucleus, and the streaks down to the bottom left corner are the tail of the comet. And this particular comet has multiple tail streaks. This is not uncommon. So the comet is standing out rather clearly in this image. In contrast, the background stars are smeared out into streaks. And the reason why this happens is that the comet is moving at a different speed with respect to the star background. So if you want to capture a really good image of the comet, which isn't smeared out, then you have to accept that you're going to be tracking with your telescope at a rate which isn't sidereal, at a rate that is special to that comet and to what its orbital elements dictate. The diagonal field of view of the image that I'm showing you is about 3 degrees, so this comet has a long tail. This is 6 times the angular diameter of the Moon. This is also a very faint tail. The exposure time for this image totalled to 45 minutes. Now if I zoom in on the head of the comet and its inner tail, you can see what very straight linear features the tail filaments are. These are always pointing away from the sun in the way that I described in my 4th lecture, Shapes of Freefall. In addition to tailed comets, the Chinese also had words for fuzzy stars. That's a comet without a tail. You can see on the previous slide how fuzzy the head of the comet is. So that's a fuzzy star. But in addition, the Chinese also had the name a guest star. and this name was reserved for a supernova or a nova explosion. In other words, a star that has newly appeared. The Chinese seem to absolutely excel at recording nova and supernova explosions. The supernova that they observed in 1054 gave rise to the debris which spread out to give the shape that you see in this image. This is known as Messier 1, or the Crab Nebula, and at its heart is the Crab Pulsar. A pulsar is a special kind of pulsing radio beacon, discovered by Jocelyn Bell Burnell a mere 4 decades ago, and I'll touch on that discovery a little more later. What we see today, this supernova remnant, is still expanding. If you take time-lapse images in much the same way that I described in the context of eclipses earlier, of this supernova remnant over years and decades, then it will be seen that the supernova remnant gets larger and larger as it still continues to expand. The Chinese didn't merely excel in recording rhythms and patterns in the night sky, they were superb at the discovery of the sudden and the stochastic. Why was this? Was it simply that they were very attentive and very meticulous? Was it simply that they had the right tools? They had loads of observatories. Was it, I wonder, because the Chinese as a culture have had the expectation of change, changing from one dynasty to the next, and so they were on high alert for change? Let me show you now some before and after images for what happens when a supernova goes off in a nearby galaxy, such as Messier 82 as shown here. And here are some before and after images of the supernova that exploded in February of 1987 in one of the nearby satellite galaxies of the Milky Way, known as the Large Magellanic Cloud and named after Ferdinand Magellan, the Portuguese explorer I mentioned earlier. Any change to the light profile of a much more distant galaxy can only be due to a supernova explosion. You can only get that sort of tremendously rapid increase in luminosity if you actually have a star explode as a supernova. Even today, amateurs can discover supernovae, sometimes by eye, more often with a relatively modest telescope, say with an aperture the size of a dinner plate. The most remarkable example of an amateur who has discovered 41 supernova explosions in the night sky is Bob Evans in Australia. At having discovered 41 such supernova explosions, he holds the record for the individual who's discovered most supernovae. How did he do this? Amazing attentiveness, the expectation that the night sky somewhere, sometime would have new supernova explosions, and a prepared mind that knows the shapes of over 1,500 galaxies really well. So when their light profile, their bright distribution changed because a supernova had gone off, he could recognize it immediately. Fortune favors the prepared mind. That applies to the supernova discoveries of the Reverend Bob Evans. It applies to Jocelyn Bell Burnell in her discovery of pulsars. Her discovery of pulsars was not expected. She did not set out to discover objects in the celestial sphere that pulsed, that gave off repeating radio signals. She was searching for something completely different. But she understood what was the signal and what was the noise. Even as a tender young graduate student, she had that important combination of a prepared mind and tenacity. I will discuss this in a Gresham lecture next year entitled Cosmic Vision, Watching the Radio. Jocelyn confounded expectations and searched with exquisite thoroughness, and she made the discovery. What else? What other discoveries does fortune favours the prepared mind apply to? Well, I mentioned this in the context of Louis Pasteur. He was the person who originally pointed out that fortune favours the prepared mind. It's thanks to Louis Pasteur that we have a rabies vaccine. It is no longer necessary in this world that people die of the rabies disease. Many searches are on today for a new vaccine. Some of these strategies will be to modify existing vaccines for other diseases. Other strategies will be based on trying to deduce something from the RNA of the virus. Others will be trying to understand how to interrupt how the virus attacks a cell wall. We don't know. It is not knowable a priori which one will work. I remind you of that Einstein quote again. If we knew what we were doing, it wouldn't be called research, would it? So discovery. How do we see what's there? The history of science shows that when you're researching something, looking for a particular signal, trying to discover something you've been planning for years, often you end up discovering something else. One such example relates to the study of merging black holes. In pursuit of the radio signature of merging black holes, a very important discovery was made. That discovery is the means by which a good many of you can watch this video lecture today. It's the means by which I can communicate with my dad during this time of confinement because of COVID-19. It's the Wi-Fi 802.11 protocol. How did this fit into the discovery of merging black holes? In pursuit of trying to develop interference suppression algorithms for the radio signals which were predicted to arise from merging black holes, some clever radio astronomers in Australia, led by John O'Sullivan, developed what we now know as the Wi-Fi 802.11 protocol. And thanks to this protocol, we have Wi-Fi communication today. This lockdown would be vastly worse without the internet. I talked about the importance of evidence earlier in my talk. The process of scientific discovery and research advance means that we are constantly confronting our understanding with new evidence. As I said in a previous lecture, quoting Maynard Keynes, in the light of new information, we change our minds. And so this means that science self-corrects. Ignorance, of course, doesn't self-correct. Because science doesn't go in straight lines, because you often don't discover what you expected to, this is why you need a multitude of approaches. This is why humanity needs a wide science base, and a scientifically literate society is key to a healthy society. Scientific discovery isn't something you can always make happen in a particular way. The history of science teaches us that the unexpected frequently happens. Fortune favours the prepared mind, as Louis Pasteur said. You need to know all the science necessary and be well informed for recognising an unexpected occurrence, be they predictable over long time scales, for example, climate change, or stochastic and sudden, the appearance of a plague or pandemic. How do we serve science faithfully to society? It's important not to speak in sound bites. The plural of soundbite is not science. Science involves holding lots of ideas together in your head at the same time and piecing together all the evidence, even that which is seemingly contradictory. Change can be understood, anticipated, and mitigated by prepared minds. It's very important in the context of change, where here on planet Earth we have long-term warning, and I'm thinking particularly here of climate change. It's also important in sudden and stochastic change, and I'm thinking here of pandemics. Perceptions, expectations, and discoveries. How does science advance, particularly in matters that pertain to safe and healthy living for everybody on planet Earth? Critical thinking matters, and I encourage you to listen to the lecture of that title by the Gresham Professor of Business on how to deal with misinformation, how to overcome the temptation to accept the views that we agree with and not consider any others. He talks about the danger of naively accepting the dangerous phrase, "evidence shows that," and not considering things any further. In the context of climate change, I encourage you to listen to the lecture on the mathematics of climate change. Being well informed helps us to understand things better and to adapt and mitigate better to the changes that we face. And we scientists don't give up because it's hard. Thank you.